Welcome to our video lecture on ionic bonding and nomenclature. Our essential understanding for today is that ionic bonds are electrostatic forces of attraction. We've just got stuff kind of stuck together, and the things that are stuck together are oppositely charged ions. This is why we call it ionic bonding. Our objectives for today: we're going to define compound and describe how those compounds form. We're going to focus in on ionic bonding and talk about how oxidation states relate to ionic bonding. We're going to understand how to name ionic compounds and how to write formulae for ionic compounds. We're going to look at these special cases of polyatomic ions and transition metals. So compounds, what even is a compound? Two or more elements that are chemically combined, super important that we have those chemical bonds chemically combined in fixed proportions. This just means they don't change. So if I have water is always going to be in a ratio of 2 to 1. Those proportions of hydrogen to oxygen will always be 2 to 1. It's fixed. It cannot change. If I change it, now it's like H2O2, that's not water anymore. Why even do elements combine into compounds? The reason is this cool thing called the Octet Rule. Atoms are most stable when their valence energy levels are full. Basically, they want to have electron configurations like the noble gases. They want to have that outermost energy level, the valence energy level, should be full of electrons. Remember that the first energy level can only hold 2 because there's only an s orbital in that first energy level, which means there's only space for 2 total electrons. So helium here is stable at 2 electrons, but the subsequent energy levels can hold 8. Which is why we call it the Octet Rule. When we're counting those 8 valence electrons, we're only counting the s and the p. We can get 2 in s and 6 in p. Those guys add up to be the valence electrons. Here I have neon. Neon has 2 s's and 2, 4, 6 p electrons, which adds up to 8, hence the Octet Rule. So how even do elements combine? One way is in molecular compounds, which is not what we're talking about today. But in molecular compounds, electrons are shared in what we call covalent bonds. Water is an example of a molecular compound. Here you can see electrons being shared. This is hydrogen's electron, this is oxygen's electron, but they're being shared between hydrogen and oxygen. Same thing in this bond over here. So in our molecular compounds, covalent bonds, electrons are shared. We're actually going to focus today on this idea of ionic compounds. We'll come back to covalent later. So in ionic compounds, some elements are going to steal electrons from other elements. We're going to have this super cool transfer of electrons. When those electrons are transferred, the result is ions. Ions have charges, and when we have opposite charges, these guys are going to stick together in those electrostatic forces of attraction. Remember that cations are positively charged and anions are negatively charged. This little animation is showing us the formation of a bond. I have a sodium 1 valence electron here. It's transferred over to fluorine. And now, because sodium is missing an electron, it's positively charged. And because fluorine has gained that electron, it's negatively charged. So again, here we see that electron move from sodium to fluorine. Sodium is now positively charged, fluoride is negatively charged, and those guys stick together because of those electrostatic forces of attraction. Opposites attract. And again, positive and negative attract. This is an ionic bond. Which is why the joke is super funny. The name's bond, ionic bond, taken, not shared. Get it? Because the electrons are taken. In covalent bonds, they're shared is funny. All right. So ionic bonds are almost always going to form between metals and non-metals. So we'll have something metallic that's going to have a positive charge, something that's a non-metal, it's going to have a negative charge, and then those opposites will attract. Remember that metals are on the left side of the periodic table. There are so many of them. Our nonmetals are in that top right corner, except for hydrogen, which is weird. He's over there. These guys, there are fewer of them, but we still put them into lots and lots of compounds. Then we have our metalloids here in the middle. Metalloids are cool because sometimes they can act like metals and sometimes they can act like non-metals. So we just have to be careful what kind of compound we're looking at to figure out if these metalloids are acting like metals or non-metals. So we're going to think about valence electrons and how those valence electron numbers relate to oxidation number, which we also call that charge of the ion, right? So if I'm looking at beryllium, beryllium has 2 valence electrons. Remember that octet rule, they want to get to 8. Beryllium has 2 valence electrons. Do you think it's easier to lose 2 to get rid of that outermost energy level? Or is it easier to find 2, 3, 4, 5, 6 more electrons to get to 8? Is it easier to lose 2 or find 6? It's going to be easier to lose those 2. Losing 2 is easier than finding 6. So when we lose 2 electrons, remember that electrons are negatively charged. If I lose them, we have a minus minus. That turns into a charge or an oxidation state, positive 2. So beryllium will become a cation. Cations are positively charged. That charge will be plus 2 because there are 2 valence electrons that beryllium wants to get rid of. Let's look at sulfur. So sulfur here has 1, 2, 3, 4, 5, 6. 6 valence electrons. Do you think it's easier to get rid of 6 or find just 2 more? Yes, we're going to gain those 2 electrons to get to 8. Our octet rule of 8 is great. So when sulfur gains 2 electrons, we're going to add things that are negatively charged, 2 of them. That charge or oxidation state is going to be negative 2. Sulfur will become an anion. Let's look at potassium. Potassium has this very one lonely valence electron. 1 electron. Easier to lose 1 or find 7 more to get to 8. We're definitely going to lose that 1. Ooh, that's a weird one. When I take away that thing that has a negative 1 charge, minus minus makes a plus. And so this potassium ion is going to have a charge of plus 1. It will be a cation. One more guy. Let's look at chlorine. Chlorine has 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Easier to get rid of 7 or gain 1 more to get to 8. And of course, it's going to gain 1. When we add one thing that's negatively charged, our charge is going to be negative 1. That's the oxidation state or the charge. And chlorine will turn into an anion with a charge of negative 1. Where do you suppose chlorine is going to find this 1 electron? Perhaps potassium that wants to give it away. And then those oppositely charged particles will be attracted to each other. So once we know our oxidation states, we can put our compounds into formulae. Chemical formulae is a way that we can represent compounds, and those formulae are just going to show the kinds and the numbers of atoms in the smallest representative unit of the compound. When I'm looking at something like water, our covalently bonded water molecules, we have 1 O and 2 H's, and so the formula will be H2O. This is water. In glucose, this is a glucose molecule, there are 6 carbons, 12 hydrogens, and 6 oxygens. In one molecule of glucose, we're going to keep all 6 of those carbons and 12 hydrogens and 6 oxygens. And so even though I could divide all these numbers by 6 and get to C1H2O1, this is not the molecular formula for glucose because I want the unit of the compound, and it's going to be a glucose molecule, which means that I need 6 and 12 and 6. So this would be the molecular formula for glucose. Now, ionic compounds, where we are transferring electrons, are different. They don't really make molecules. So in that water, we had the H and the O and the H, and this made one complete water molecule. With our ionic compounds, we don't really have molecules. Instead, we have what we call a lattice structure. And this idea of a lattice, that's L-A-T-T-I-C-E, this lattice structure, what happens is I have a chlorine anion, we're going to call it chloride, and it's going to be attracted to the positive sodium ion, which is also attracted to a negative chloride ion, which is also attracted to sodium, which is attracted to that negative anion, and then positive, and then negative, and then positive, and then negative, and it just keeps going on indefinitely. When I have these chunks of lattice structures, we end up with crystals. And this is why most of our ionic compounds, which we sometimes also call salts, are crystalline when they are solids. we don't have just one sodium and one chlorine to make a salt molecule, but instead I have this giant, indefinitely large, going on and on structure that is a lattice. And so in this particular picture, I have 16 sodiums and 16 chlorides, but 16 and 16 is not going to be my ionic formula. In ionic formula, we always go down to the lowest terms. I can divide both of these guys by 16, and I'm going to have sodium 1, chloride 1. My formula unit, so I'm not going to call it a molecule, but instead of formula unit, will be sodium 1 to chloride 1, 1 to 1. Let's look at how to name ionic compounds. So if I'm looking at a compound that's binary, so that's only two elements in it, one cation, one anion, we are going to start with the cation name first. If I have lithium in the compound, lithium's name would come first, cation first, and the anion is going to come second. We're going to change the end of the ion name to ide. So if I was making a compound between lithium and bromine, lithium would stay the same. We would just call it lithium. But bromine, we would change the end to bromide. So instead of ene, ide. And the compound's name would be lithium bromide. Let's do lots of practice. So calcium sulfide, calcium's our metal. It's going to start first. Let's write the formula for this guy. We would start with that Ca for calcium, and then sulfide is coming from sulfur, which is a capital S. So this would be the formula for calcium sulfide. Pause the video, try the next three on your own, restart the video, and check your work. All right, so hopefully you got aluminum is Al, phosphide is capital P, aluminum phosphide. Rubidium bromide, rubidium is Rb, capital R, lowercase b. Bromide is capital B, lowercase r, so Rb, Br. And then magnesium oxide, Mg, capital M, lowercase g, capital O. Let's do the opposite. Now we're going to take these formulae and turn them into names. So NaCl, Na is sodium, Cl is chlorine. We're going to change that chlorine to chloride, sodium chloride. Once again, pause the video, try these next three on your own, come back and check your work. All right, so BeO should be beryllium oxide, change oxygen to ide, oxide. K2O, it doesn't matter that that 2 is there. We'll talk about why those are there later. For now, just know that K is potassium. Its name doesn't change, it's the cation. Oxygen, once again, turns to oxide, oxygen to oxide. And one more, aluminum, or aluminium if you are from Britain, and that F is going to turn into fluoride instead of fluorine. Sometimes we have more than two elements in our ionic compounds. And the reason is these super cool things that we call polyatomic ions. What happens is we have some covalently bonded nonmetals. I have an oxygen and a hydrogen here. These guys are sharing some electrons, but then they work together to go steal somebody else's electron. So they're ions because they are transferring electrons. They have that charge. But instead of just one nonmetal, we have multiple nonmetals that are sharing electrons with each other, but then go steal somebody else's. Let's look at some compounds that have polyatomic ions. You do not need to memorize the names of these guys. Instead, you're going to find your handy-dandy periodic table. There's a list of common polyatomic ions on your reference materials. If you don't have those handy, pause the video, go grab them, and come on back. We're going to look at how to name these guys. So, assuming you've got your list of polyatomic ions ready to go, calcium carbonate, I'm going to write the formula for this. Calcium is still just capital C, lowercase a. That's the symbol for calcium. Carbonate. 8 ends in an 8, not an ide, which means that I'm going to look at my list of polyatomic ions. Carbonate's right here. This is the formula, CO3. This guy here is the charge. It has a charge of -2. We're going to write the formula, the whole entire formula, including the numbers, in the formula, but we're not going to put the charge into the formula. So it'll be CaCO3. Again, I'm keeping the subscripts there on the bottom. I'm going to keep the 3 but I'm not going to put the charge in the compound's formula. Let's look at sodium hydroxide. This one's kind of tricky because it does end in "ide," which is kind of like what we did to our elements that were anions. But hydroxide is hydrogen and oxygen together. It's this polyatomic ion right here. Hydroxide is OH with a -1 charge. So I'm going to write sodium. Sodium's symbol is capital N, lowercase a, and then hydroxide will be capital O, capital H. Again, we're not going to include the charge in the final formula. One more. Let's look at potassium nitrate. Potassium is oddly capital K, right? Not a P. Nitrate is here, nitrate. Be careful, we have an 8 and an ite, so pay attention to those details. Nitrate is NO3, capital N, capital O, lowercase 3, subscript of 3. We're not going to worry about that charge in the final formula. So KNO3 is the formula for potassium nitrate. So now we're going to add a little bit more detail about why those couple slides ago, the formula for K2O potassium oxide had that 2 in it. When we are writing formulae for ionic compounds, they need to have a net zero charge. What that means is that the number of positive ion charges has to balance the negative ion charges. That's easy for some compounds like sodium chloride. I have sodium has a charge of +1, chloride has a charge of -1. +1 -1 balances out to 0. We have that net charge of 0. So our formula for sodium chloride would just be 1 Na and 1 Cl. But sometimes those charges are a little bit different. So magnesium's oxidation state is a +2. It's an alkaline earth metal. Its charge, its oxidation state is a +2. Fluoride's charge is only a -1. It's a halogen. It's a -1. +2 and -1 do not balance each other out to a 0. So what happens is that +2 magnesium needs not just 1, but 2 fluorides to balance out those charges. So I would write my formula as MgF2 so that I have 1, 2 negative 2's and 1 positive 2 +2 -1 -1 will balance out to that 0. For every 1 magnesium ion, I need 1, 2 fluoride ions in the structure. Let's practice writing some formulae by balancing those charges, finding that net charge of 0. So our first example here, Pb2 plus NCl -1. I have lead with a charge of +2, chlorine with a charge of -1. If there's not a number there, we're going to assume invisible 1. So +2 -1, these guys don't balance out yet. I need another -1 so that +2 -1 -1 balance out to 0. To do that, I need 2 of those chloride ions. So my formula will be PbCl2, 2 chlorines to every 1 lead, so that I have -1 -1 +2. Let's look at the next one, aluminum and fluoride. Aluminum has a charge of +3, fluoride is a -1. To balance those out, I need 3 of these guys. Fluorine times 3, 3 times -1 will be -3. And then over here, I have a +3 that balances out to 0. And so our formula will be AlF3. Potassium and selenide. Potassium's a +1, selenide's a -2. Let's balance it out. I have a +1, -2. I need more pluses to balance out that -2. If I have 2 of these, 2 times +1 is +2, +2 -2 balance out. So our formula will be K2Se, 2 potassiums, 1 selenide. Let's do one more together, Sr2 plus and P3 minus. I want to balance out the +2 and the -3. The easiest way to do this is to think about our least common multiple of 2 and 3. The least common multiple of 2 and 3 is 6. 2 times what is 6? 2 times 3 is 6. So 3 times +2 is +6. On the phosphorus, 3 times what is going to give us 6? It's a 2. So if I have -3 times 2, that's going to give us -6. Plus 6 minus 6 balance each other out. And so our final formula is going to be Sr3P2, 3 strontiums and 2 phosphides. The next 4, I want you to pause the video, do them on your own, come back and check your work. Hopefully you have some work ready to check. Aluminum and sulfur is going to be Al2S3 because aluminum times positive 3 is a plus 6, and then sulfur times negative 2, 3 times negative 2 is a negative 6. Potassium and hydroxide, this is a polyatomic ion hydroxide with a -1 charge, +1, -1, they already balance each other out. So it's just going to be KOH, potassium hydroxide. Cu with a 2+ charge, nitrate with a -1 charge. I need 2 of these guys, -1, -1, to balance out this +2. This one's going to look kind of weird if I write CuNO3 2, it's going to look like I have 32 oxygens, and that is not what we have going on. So what we do is we actually add parentheses around the nitrate, and that shows us that we have 2 of those nitrate polyatomic ions for every 1 of those copper ions. All right, one more. I have aluminum 3+ and carbonate 2-. We're kind of looking at this problem again where we have a +3 and a 2-, least common multiple is going to be 6. So I need 2 of those because 2 times positive 3 is a positive 6. I need 3 of these because 3 times negative 2 is negative 6. Positive 6, negative 6 balance each other out. So our formula will be Al2, carbonate 3, CO3, but I need 3 of those. So I'm going to show that with parentheses. Remember a long time ago we talked about those oxidation states, those charges, and alkali metals are always +1 and alkaline earth metals are always +2, and I said we're going to skip the transition metals because they're weird. Well, this is one of the ways that they are weird. Some of them can have more than one oxidation state, more than one charge. Copper can be +1, but it can also sometimes be +2. So how we know which charge, +1 or +2, to use for copper, we're going to add Roman numerals. So copper Roman numeral 1 has a charge of +1. The Roman numeral tells us the charge. Copper Roman numeral 2 has a charge of +2. That +2 tells us the charge of this copper. So if I'm writing a formula for copper 1 fluoride, this copper has a +1 charge. Fluoride is a halogen, it always has a -1 charge. So I have +1, -1, this balances right out, easy peasy. It's going to be CuF. This is going to be our formula for copper 1 fluoride. Copper 2 fluoride, well, now this copper has a +2 charge. Fluoride only has a -1 charge still. It's a halogen, it's going to always have a -1 charge. +2, -1, this doesn't balance out. But if I have 2 fluorides, 2 times -1 is -2, -2 and +2 balance each other out. And so my formula for copper 2 fluoride is going to be CuF2. Be careful. The easiest mistake to make is to think that this 2 means I need 2 coppers. Cu2F. This is wrong. Don't do it. Notice that the 2 is actually on the fluoride, not the copper. That copper 2 means that copper has a +2 charge. Fluoride has a -1 charge. To balance those out, we need 2 fluorides. 2 more examples, my friends, and then we're going to call this a day. Sometimes these ions with multiple charges, our transition metal compounds, make super cool stuff. Iron 3 phosphate is a compound found in slug bait. So if you have slugs in your garden that are eating up all your leafy vegetables, you can throw some iron 3 phosphate into your garden and kill off those slugs. Iron 3 phosphate, how are we going to write the formula for iron 3 phosphate? Iron's symbol is Fe. This Roman numeral 3 tells us that this iron has a charge, an oxidation state of +3. Phosphate, it ends in an 8, so it's a polyatomic ion. I'm going to look at my list of polyatomic ions. Phosphate's formula is PO4 with a -3 charge. Something magical is happening here. Look at my charges, +3, -3. They balance out. I don't need to scale anything up. Our final formula is going to be FePO4. That's it, just one of each of those guys. Those charges balance out. Remember, we don't put the charges in the final formula. And then one more problem, tin, Roman numeral 4 oxide, tin 4 oxide. We use in paint glazes. So if you're into ceramics, you probably use a lot of transition metal compounds in your paints, in your glazes. So tin 4 oxide, tin oddly, its symbol is SN. Roman numeral 4 means that this piece of tin has a charge of +4. Oxide is coming from oxygen. Oxygen is in group 6A or 16. It has a charge oxidation state of -2. +4 and -2 do not balance out. I need 2 of those oxygens. 2 times -2 gives us -4. -4 plus 4 balances out to 0. And so our final formula is going to be SNO2 because I need those 2 oxygens. And my friends, we have accomplished our video lecture on ionic bonding. Remember that ionic bonds are those electrostatic forces of attraction. We have stickiness because these ions have opposite charges. They stick together in those lattice structures. Our objectives were to define compound, elements bound together in chemical bonds in fixed ratios. We talked about how compounds form. Electrons can either be shared or transferred. We defined ionic bonding. It's that definition right there. Oxidation states come from gaining or losing electrons to get to that octet rule. We talked about naming ionic compounds. We talked about writing ionic formulae, balance those charges. Polyatomic ions, you have a list. Check that list for all those polyatomic ions. Transition metals, Roman numerals, Roman numeral 2 or 1 or 4 or 3 or 6 are going to tell you the charges of those transition metals. Good work today.